Hey everyone, this is Nick, and this section is all about functions on real numbers, so functions that have the real numbers as a domain. Just a recall of what we did last time. Last time we learned about functions with any arbitrary domain x. Domain, remember, is the same as set of inputs, and out of the function came a set of outputs, y, and the set of inputs, x, was sent there by our function little y, such that for each input little x, only one thing comes out of the function, and the thing that comes out is the output y of x. So that's what we talked about last time. This time, our functions will have domain, the real numbers, and also the set of outputs will be the real numbers as well. So we're going to learn about how to draw functions like that. So let's begin by taking a quick look at the real number line. So this is the set of all real numbers. Goes on forever in that direction and forever in that direction. Usually we put 0 in the middle. And on this side, I guess we got 1, 2, 3, 4, and so on. -1, -2, -3, -4. And so, yeah, because it goes on forever in both directions, clearly this is an infinite set of numbers. There's infinitely many of them. Goes on forever. But not only that though, I'd just like to draw to your attention, take any two numbers. I've chosen 0 and 1. There are infinitely many numbers between 0 and 1. All of these guys here are real numbers, and there are infinitely many of them. For example, in the middle of 0 and 1, we got 0.5, which is the same as a half. Now in the middle of 0 and 0.5, we've got 0.25. So 0.25 is halfway between 0 and 0.5. Once again, we can take the middle of 0 and 0.25. See if I can draw it properly. Yep, got a pretty good one. So this is, well, what's 0.25 divided by 2? 0.125. So that's halfway between 0 and 0.25. My point is, we can keep doing that forever. We can keep cutting it in half forever. So there are infinitely many numbers just between 0 and 1 alone. So actually, for the same reason, there are infinitely many numbers between any two other numbers that you pick. So there are infinitely many numbers between whatever's here and whatever's here. That's a lot of numbers. That's all I'm saying. So, well, why am I telling you this? The reason why is because our old diagram, remember we used to draw diagrams like this. We'd say here's our domain, here are our inputs. Maybe there's 4 of them this time. I don't know, I like to do it with 4 inputs. Obviously there can be more or less. And here's our set of outputs, the things that come out of the function. Maybe there's 3 of them. And then our function little y took this input, sends it to that one. This input sends it to the same one. This input is sent to this output, and this input is sent to that output. Well, that immediately tells us what our function is. For each little x, we know exactly what y of x is. We know exactly what our function does to that input. That's all well and dandy, but this only works because there are 4 elements in our set x, and there are only 3 outputs in our set of outputs y. So if we did it for the real numbers, where the real numbers are the set of inputs and outputs, there's going to be infinitely many and infinitely many, and there's going to be a lot of arrows, and it's just not really going to work very well, is it? So we need to come up with another way. Well, actually, we don't need to. Somebody's already done it for us, thankfully. So we're going to learn about exactly what they did. And here's how it works. So this is the real number line. Here's 0. Okay, so this is the real number line. Our function little y takes the real number line. It takes in a real number and it sends out a real number. It spits out a real number. It takes the real numbers and sends them to the real numbers. So our domain is the real numbers and the set of outputs is the real numbers. How do we represent this as a picture? Well, what we choose to do is actually draw another real number line. So this is also a real number line. This real number line here, this one represents our set of inputs. So we call it x, because remember, x stands for input. X is the, well, our inputs are always written as little x for some reason. So we call this real number line, we call this one the x-axis. These are the things that go into our function. And this real number line, this vertical real number line, we're going to call y, which stands for the, where do I write this here? Y-axis. These are the things that come out of the function. These are the outputs. Y is also short for y of x, the things that come out of the function. All right, let's fill in some numbers. Here's 1, here's 2, here's 3, here's 4, so on. -1, -2, -3, -4, so on. For our vertical line, up is positive. So this is 1, this is 2, this is 3, this is 4, and this is -1, -2, -3, and so on, forever in both directions. So, how do we draw our function? Well, we don't know what our function is yet, so let's come up with an example of one. So our function y sends the real numbers to the real numbers, as we know, and it does it like this. We have y of x is equal to, let's say, x plus 1. It's similar to the function we looked at in the last chapter, but it's also different because this time our function takes in the entire real numbers. So you can put any real number you want into this function. Before, we only looked at the real numbers 1, 2, 3, and 4. We only put them into our function. This time we're putting all the real numbers into our function. So our function takes an input x and spits out x plus 1. It spits out the output 1 bigger than whatever that input is. Okay, so how do we draw this as a picture? It's actually nice and easy. What we do is we just plot the points. So for each of our inputs on the x-axis, we go to it and we say, okay, this is our input, and then we go up. And we go up until we reach our output. Where is the output? Well, y of 1 is equal to 1 plus 1 is equal to 2. So here's our output here. This is the line, by the way, use a different color. This yellow line here, this is the line x equals 1. Along this line, x is equal to 1 everywhere. Our input x is equal to 1. This line here is the line y equals 2. The line y equals 2, because everywhere on this line, our y value is equal to 2. Well, we want the point where x equals 1 meets y equals 2, because x is the thing that goes into the function and y is the thing that comes out of the function. Well, we can see from our picture that that point is actually right here. Right here. This is the point 1, 2. Because the thing that we put into our function is x equals 1. The thing that comes out of our function is y of x, or y equals 2. So that point represents the value 1, 2. It means we put x equals 1 into the function and 2 comes out of the function. I'll clear up some space. You can do the same thing with actually all of the points. For example, y of 2. Well, yeah, let me do it down here. Let me write it down here. Y of 2 is equal to 2 plus 1, which is equal to 3. So if we put 2 into the function, the thing that comes out should be 3. So we want to find the point where the line x equals 2 meets the line y equals 3. And that point clearly is right here. So this point represents, well, this is the point 2, 3, because our x value is 2 and our y of x value is 3. Okay, well, this is all well and good. How about 0.5? Let's take x equals 0.5. Let me choose. So this is 0.5. Okay, how on earth do we plot this? Because remember, we're not just putting whole numbers into our function, we're putting all the real numbers into our function. So 0.5 is one of those numbers. Okay, well, y of 0.5, let's work it out over here. Y of 0.5 is equal to 0.5 plus 1, which is equal to 1.5. So, same as before, we go up vertically along the line x equals 0.5, and then we continue until we meet, this is 1.5. We continue until we meet the line y equals 1.5, and that line meets it here. Okay, we can keep doing this forever. We can keep doing this for all of the points. And what we find is that actually the more points we plot it for, the more and more our function gets filled in. I drew this pretty badly. My point is that it's basically going to make a line. If we keep doing it forever, it's just going to end up as a line like this. And that's our function. This is the line y of x is equal to x plus 1. That's our function right there. Okay, so that's what these drawings mean. I wrote something in the notes. Let's take a quick look at that. So I made an observation here. I said, well, why does this thing have to be a line? Let's draw my axes. This is my x-axis. This is my y-axis. So why does the function, let me draw it, y of x equals x plus 1, why does that have to be a line? Why does it make sense that that thing should be a line? Well, let's see, shall we? Let's take any random value x. This is the input little x. Yeah, okay. This is the input little x, and then we're going to take another input, x plus h. Well, let's take a look at what the difference is on the y-axis. So this is y of x. Now I'm claiming that this difference, well, we know that the difference down here, we know that this distance here is h. Well, I'm claiming that this one, why is this distance here h? Well, because x plus h minus x is equal to h. So I'm claiming that this one here is also h. How do I know that? Well, let's take in the point that we know that this point here is y of x plus h. Well, y of x plus h is equal to x plus h plus 1. Because y of x is equal to x plus 1 for any input x. So y of x plus h is equal to x plus h plus 1, but x plus h is equal to y of x. So this is equal to x plus 1. This is equal to x plus 1 plus h. You know, just flipping the h and the 1 around. That's fine, because addition doesn't matter what order you do it in. But y of x is equal to x plus 1. So this is actually equal to y of x plus h. So this is the point y of x plus h. And so this distance here is also h. So no matter whatever small amount you increase x by, y is going to increase by that same small amount. So it makes sense for this thing to be a line if you think about it. Do functions always have to be a line? Do functions on the real numbers with outputs in the real numbers always have to be a line? Well, The answer is of course no. No, they don't. Let's take one real quick example. So this is our x-axis. This is our y-axis, and we're going to take a look at the function. We're going to take a look at the function y of x is equal to x squared. We're going to have a look at what that looks like. Okay, well, yeah, let me go back to black. Here's 1, 2, 3, -1, -2, -3. And obviously 0 is in the middle. Okay, well, what is maybe I should do something vertically as well. 1, 2, 3, 4, -1, -2. Okay, enough of that. Clearly, y of 0 is equal to 0 because 0 squared is equal to 0. So y of 0 is equal to 0, and that means we're going to be putting the point 0, 0 on our graph. How about y of 1? Y of 1 equals 1 squared equals 1. Okay, so that's our point there. So far, it looks like it might be a line. But then we take y of 2. Y of 2 is equal to 2 squared, and 2 squared is 2 times 2, which is 4. So y of 2 is actually equal to 4 all the way up here. Wow, okay. How about 1.5? What is y of 1.5? That's equal to 1.5 times 1.5. 1.5 times 1.5 equals, so 2.25. Okay, so 2.25 I guess is about there. And you'll find if you fill in the whole thing, it actually makes kind of a curve like this. Makes a kind of a curve shape. 3 squared is 9, so that shoots all the way up. What about the other side? Well, -1 squared. So -1 squared is actually also 1. So y of -1 is also 1. In fact, it's a reflection, because when you times a negative number by itself, it's the same as when you times a positive number by itself. So -2 squared is also 4, because -2 times -2 is also 4. And similarly, -1.5 is equal to 2.25. And so what it should look like is the same on either side of that y-axis. But in particular, notice that it's not a line. Okay, that's all I got to say for this section. Make sure you check out the notes and do the exercises at the back. Thanks very much for watching. See you next time. Take care.